called transverse relaxation, and the other one longitudinal relaxation. So when there is no ensemble, when you take for certain transition between some level 1 and 2, for example, you can write it as the magnitude of this transition at time 0 times the time dependence, which is absorbed in this exponential factor. But with an ensemble, you have to sum over all members of the ensemble, and that's what the letter J stands for, which with a little bit of math we turn into an integral over epsilon 1, 2, where epsilon 1, 2 varies now because every member of the ensemble has a different energy of excitation, slightly different. That was the big assumption. We didn't derive this, but it makes sense to assume that. So for transition 1 to 2, for example, for proton 1, for proton 2, 3, 4 ion or proton. So this defines this D interval this is an interval in energy. This is a famous picture by Dr. Dmitry Killing. Then we ran some MATLAB code written again by Dr. Killing that shows the complex phase of our expansion coefficients as a function of time for each member of the ensemble. And in this particular code, we had 40 ensembles. The black line shows the complex phase in the isolated single molecule. But when we added many other members of the ensemble, where omega was randomly shifted, the interval was the same between each member, but I guess we just picked some number to shift each energy level between the 40 members of the ensemble, and it looks like the shift in the energy is the same because the change in the oscillation of the complex phase is the same. But anyway, so this shows black line, isolated molecule, many colorful lines, many molecules in our ensemble. So when we have the ensemble, the system eventually, the pulse excites the system, and the pi/2 pulse creates these half occupation levels. So the observable is the same, but the complex phase is different.